for the following functions. Evaluate for the given value, show all work. Okay, so they're already telling us that something's a function. When we know for sure that something's a function, that's the time it's okay to replace any y that you're used to seeing, the letter y, variable, with f of x. That means it's a function of x, a function with respect to x, such that x is a variable on the inside. These are all in terms of x. And we have 3 examples, and we just want to watch that we're doing our order of operations correctly and we understand what's going on. So for this first example, we want to find the f of negative 13. So normally the notation says f of x. It wants us to do f of negative 13. Everywhere we have an x, we're going to plug in a negative 13. So that'll be 2 times negative 13 plus 5. Now I keep showing the work the same way. I hope that you show it the same way when you're taking any type of an assessment or turning in any work. 2 times negative 13 is negative 26 plus 5. And for my last step, I'm going to write it out full statement. F of negative 13 equals negative 26 plus 5 is negative 21. So for yourself, you may want to recognize that this right here is an x value. This right here is a y value. We should also know the other words. We can use input, output. We can use this is my independent variable, dependent variable. We can say negative 13 is part of my domain, and negative 21 is a part of the range. For the next example, we have to watch out. We have a negative in front of the x squared, and here in the third one, we have a 3 in front of the x squared. So we want to make sure we're doing these correctly. So over here, we're going to do f of negative 4. Always think about that being an x. Next line, I'm going to write that f of negative 4 again. I don't care if you think like, oh, it's not necessary or I don't feel like it. You really should, okay? Also, don't get sloppy and lazy with your negatives because they tend to disappear when you guys do that. So please be very careful of that. Negative. Now, in the parentheses, we have a negative 4. We square it. Negative 4 squared means you multiply by itself. So negative 4 times negative 4. That becomes a positive 16. And this negative on the outside makes it a negative 16. This is a big area for error, so be careful. 4 times 4. Also, I see a lot of carelessness for 4 times 4 becomes 8. So please be careful. We have 16 and minus 6. 16 and 16, if they were both positive, it would be 32. They're both negative, so it's just negative 32. And we're taking away 6 more. If you go back and watch the video for lesson 3, that can help you with some of this. There's a ton of practice examples. So if you're getting these wrong, making mistakes, and you have to correct these, I would definitely suggest going back to the 3rd lesson. F of negative 5. See, I'm even saying it out loud to myself. I'm not saying f negative 5 or f times negative 5. This is f of negative 5, the function value, the output value of the function at negative 5, when x is negative 5, is, the equal sign means is. F of negative 5 equals 111. There should be a parenthesis after that curly bracket, okay? So again, when you write a set of ordered pairs, you start with a curly bracket. You might write your ordered pairs. So maybe I have 3 random points, and then I close off my set. Graph the given relation. Now, they don't state anywhere that this is definitely a function, but I guess this is for us to find out. If you look below at question C, they are asking us to find out. The ordered pairs. Sometimes people mix these up, so you have to know the difference between x and y. Right away, that immediately answers my question of, is this a function? The answer is already no. Okay, it's going to fail the vertical line test. A single input value cannot go to more than one output value. Be careful with the ordered pairs with zeros. I feel like that's where everyone gets very, very careless and puts them on the wrong axis. So 100%, please be careful. Represent the relation with a mapping diagram. In the mapping diagram, we're going to map an input value to an output value. The arrows will point from the input to the output, and there should be no question about what numbers we're connecting. Sometimes it's easier to go from the graph, and for x, I'm going to move from left to right and fill those in. And then for my y's, my outputs, I'm going to move from the bottom up to the top and fill those in. I'm going to connect these with the arrow. Some people were connecting them like with a little line segment from the outside of the box to the outside of the box. Now is not the time to be creative and innovative and come up with your own ways for designing something. There's a right way and a wrong way to do this. Negative 9 should go to 4. I should not have any confusion about negative 9 going to 4, and the arrow must be on the right-hand side. So I'm really starting right up against it so I can see clearly, okay? The negative 6, I'm looking up here. Negative 6 should be going to 8. By doing this also, like checking up here, even though I made it from here, it's sort of checking all your work because you're triangulating everything. You're tying all 3 things together. I filled these numbers in from what I graphed, and now I'm checking my ordered pairs from the original set. So if a number comes up here that I didn't write there, well, maybe now I'll catch it. Is this relation a function? Why or why not? Use appropriate notation to state domain and range. Okay, you have to use appropriate notation because otherwise you're not answering the question correctly. That would not be correct. -9 to 9 would mean that your graph is basically continuous data points. Every single value, every decimal, every little thing would be included. We cannot use interval notation in a case like this. The easiest way to do this, because I know I need set notation, I already have my values listed right over here. So those are what I'm going to use. Use the vertical line test to determine if each graph represents a function. Then use the appropriate notation to state the domain and range. You can assume that each grid square is 1 by 1. Looking at this, thinking about the vertical line test. Is this a function? Yes, it passes the vertical line test. No vertical line drawn on here will cut through the graph more than once. Now the domain. These arrows indicate that the graph is going to continue in this similar behavior in this direction, okay, and this direction as well. Now think about where this is going. Not only is this arrow going left forever, but it's also going down forever. This one is going to the right forever. It is moving to the right slowly compared to this one, and it's moving down as well, but it's moving down probably more rapidly than this one. It's steeper. But it does not change the fact that things are moving left or down, right and down, okay? Domain. For the domain, we're looking at this from left to right. The furthest left my domain goes is all the way out to -infinity. So my -infinity, I'm using interval notation for this because it's smooth and continuous, it's not discrete. -infinity is all the way to the left, comma. I'm following along this graph. I would not have to pick up my pencil, and every x value is being included. All of these x values are being used in the ordered pairs to make the points on this graph. Going, and we go to the right forever. So my domain is from -infinity to infinity. Some people like to write the symbol for all real numbers. The all real number symbol is like a double line right here, very close together, and then that's used to make an R. This is interval notation, and this represents the phrase, the set of all real numbers. Now for the range. The range, we come from the bottom and we work our way up. These are pointing down forever. My range begins at -infinity. Now, which y values are being used? Now, while this maxes out over here, this keeps going, and it looks like we max out pretty close to whatever this number is. So 1, 2, 3, 4, 5, 6. So I'm going to be a little weird, and I'm going to put 5.9 because I think it's a little bit below 6 right over here. So 5.9, which is included. If you kind of looked at it as a 6 and you wrote a 6, I'm not going to mark that wrong. Maybe you're like, you know what, I'm going to make this definitely clearly at 6. My graph is different, and I'm going to put 6. Question E just asks, explain how and why the vertical line test is a practical method for determining whether or not a graph on the xy plane is a function. So, like I've been pointing out, in the earlier question he asked if that example on the first page was a function. He said no, because -6 went to 2 y values. By drawing a vertical line, the equation of a vertical line, I'm just going to write some notes over here. I'm going to speak out the answer. You can write it down in your own words. The equation of a vertical line, this is for you guys to remember when we get to linear equation stuff later on, is, I started writing y out of habit, is going to be x equals a number. What number will it be? Well, whatever number the vertical line is passing through on the x-axis. So when you draw a vertical line, so say I drew one through x equals -1, it would go right here. Everywhere it touches, the other graph is where they intersect. By having 3 answers or 2 answers or however many answers, you're essentially finding multiple y values that correspond to that single x value. So visually, a vertical line is a very fast way to look at a graph and decide whether or not it's a function. So replay that, put it in your own words, come up with your own explanation. I just wrote down a little information about equation of a vertical line, but you can put this in your own words, okay? I'm not gonna write down a wordy answer. For this part of the activity, I have 30 boxes filled in with little expressions. So independent variable, pounds of fruit, X, number of paint cans, score of a football game, range, number of hours an on switch is activated, how much math you master, grades on your test, surface area of a fence. And I ask you to put together 15 logical thoughts from these 30 options provided in the table below. So the order you write your answers in will definitely vary. Blank depends on blank. So one example, just to get started before anything else here, one example would be that the dependent variable depends on the independent variable. The answers to this are in the video for the lesson 3 supplement. So if you go to the lesson 3 video, I did a little activity in the video where I had these pieces all cut out and I matched them and put together what depends on what. So if you want the answers to these, which I hope you do, or if you want to make sure you're right since I'm collecting this, or if you want to know if you're right because you're studying and you just want to make sure you know how to do things, just go right back to the lesson 3 video. And if you watch that, you can put it up in high speed, you'll find that in the video and you'll be able to fill out all of these answers. It is on the YouTube channel, it's in the playlist, and it's also on Google Classroom. Here we have directions that ask us to read each statement, then decide the independent and dependent variables. Fill in the blanks with the most appropriate responses. Okay, my major suggestion for this, because we did do an exit ticket with this in class, and a lot of you, I don't want to say you're being lazy, but you're really not being very detailed. You should take from the language in the question and just recycle that language here. Also, if you write y depends on x, gee thanks, that doesn't really tell me anything. The whole point of this, the big lines are not so you could tell me something I already know. I really wanted to reiterate what depends on what. Fill in the blanks. So here, the Lower Colorado River Authority measures the height of the lake after each rain. The Lower Colorado River Authority measures the height would have to do with this part right here. And it says height of the lake, prepositional phrase for us. Depends on whether or not really it rains. So they'll measure the height if it rains, okay? Now, maybe this is a very strange river, and every time it rains, the water rushes and pushes a certain way, and the height goes down. Nowhere does it say in this statement that the height of the river goes up or goes down. Maybe it's a phenomenon that the river height never changes over here, or the lake, whatever it is. The lake height doesn't change even when it rains, so they keep measuring it, and they're like, this is, outstanding, it doesn't change. So if you fill in this with, the height of the lake depends on the rain, you're really not pulling from given information. You're doing something where you're making an assumption. So do you see that I'm pulling quite literally from the information provided? So this would be a better answer. So I really do expect you to change your answers here and really think about what I'm writing. Before my dad takes a trip, he checks his gas tank to calculate how many miles he can drive. It does not say anywhere over here, the more gas he has, the further he can drive. That's not what it says. That is not what it says. Do you see? Only go based off of what it says. The teacher estimates the number of minutes a student will spend on homework when deciding how many problems to assign. If, or when I could change to if they're deciding how many problems to assign. This is my independent. That's going to happen no matter what. And it's sort of like this other extra bonus part of it is the teacher estimates the number of minutes a student will spend on homework. Okay, you want to use that exact language. You can't write like, oh, the more problems you assign, the longer it will take. That is not what it says, and that may not be true. This example is just like the last one, except we are given, instead of a compound inequality, we have an absolute value inequality. So first step is what? If you said rewrite the problem, then you're awesome. Divide by -2. When we divide by -2, this becomes positive 11, and that flips. Absolute value of 3x minus 4 is greater than 11. What do you do from here? Okay, you need to know what to do on your own from this spot. We have isolated the absolute value part of this problem. We have that it's greater than 11. We spoke about this in detail, okay? The thing inside of the absolute value has to be greater than 11, but, so I'm going to write that, the inside has to be greater than 11. So I'm going to go like this. Okay, but the inside, which I'm not touching, if you remember I did this whole thing on the board, could also be less than negative 11, because that's negative 12, negative 13, negative 14, and when I take the absolute value, guess what? It's still greater than 11. These are what I'm solving here. All right, next thing that we have is matching, but this matching got heavy crazy, and there's a lot of words and phrases that we need to organize in our heads. So it started off as just a few, and it got more and more and more. So that's why I wrote, you may choose to color coordinate and or list connected phrases in columns after. So maybe you start off by kind of playing around, reading it, and kind of connecting things to each other. But remember, you don't have to have just one pair. Things can be connected. There could be a triangle of information. There could be a whole list of information. So what I decided to do was I went into my notebook and I wrote out important words and phrases. Let's organize ideas. Now the lessons that we focused on are, one was relations and functions. Then we did a little bonus of interval notation to get us ready for 2, domain and range. Then we highlighted independent and dependent with function notation. Independent and dependent we also spoke about in our interval notation and relations and functions section, as well as in domain and range, so we were ready for it, no big deal. Function notation, we also spoke about that in lesson 1, so we were ready for it too. So this should have been pretty easy, but there was a lot of algebraic practice of evaluating from function notations. Okay, that was a big place because of the careless algebra mistakes that could happen. Lesson 4 is discrete and continuous. Again, when did we speak about that? We spoke about it in lessons 1 and 2, and while we did interval notation, so we should have been ready for it. And lesson 5 is change and rate of change, which I did speak with a couple classes about, and I put a little star here because I did really have a great discussion about it in lesson 3, both in class and in more detail in the video that I provided on Classroom. It's on the playlist on YouTube, and it's listed on Google Classroom. Okay, so I went through and I organized all the vocabulary given in the study guide, and I'd like to kind of put it together in a more organized way for everyone. So I started off by adding my own word. I added the word relation because I didn't really have it listed on there because I didn't think of it as connecting directly to other things, but that is where we started the unit. So relations. Relations relate to or more variables such as x and y. Now underneath x over here and underneath y over here, I'm going to make a list. So over here, I'm going to list other words such as input and output. I'm going to keep them moving along in a nice corresponding fashion so that we can make better associations. So I'm just focusing that a bit. All right, other words that were on the list were independent and dependent. My dog is a little bit growling to himself right now, so he might start to bark. Sorry. Now, big words that are really important are words like domain and range. So I even writing them in bigger font. Sorry, the wind is blowing, so obviously he needs to talk to the wind. So domain and range are going to let us really elaborate and use a lot of the other words in this list and break them down and describe them in detail and kind of put them into categories. So I'm going to do that underneath here. And before I do, I know that a lot of times we're a little bit too comfortable and loose with like throwing around f of x for y. So I do want to kind of elaborate on that for a moment. So I'm going to add the word function on the side over here. So, sorry, I'm going on a slant. I just want to make sure I fit it all here. So functions are special. And again, for more detail, if you need more of a definition, definitely go back to the other videos, go back to your notes. Are special relations, and only then, okay, only when we know that y belongs to a function, that is when we can call it f of x, okay? You can't just throw around f of x whenever you want. And this also, under the circumstances of functions and f of x, is when we use words like, especially these two words, input and output. We really reserve words like that for functions, okay? Function notation, evaluating functions, which you can find inside your notes, inside worksheets and packets and things like that, okay? So I'm just going to kind of put this as a little side idea. Okay, really continuing with this now. I'm going to take the domain and range, and I'm going to make my own little extra box over here. So domain and range. So the following really relates to this topic. I know if you look at the other words, you probably could already see why they do, but I'm going to separate it into a little bit of a list. One's going to be a little short, the one where I talk about set builder notation, and then when I talk about interval notation, that's going to be a little bit bigger, okay? So domain and range, things that we relate directly to this is we do not repeat values. We list them once. If they're in the domain, if they're in the range, that's all there is to it. They're there and we're done. We don't list them more than once. Also, when we're dealing with domain and range, we list, little bullets in front of this, list or describe, because not everything is going to be a list. Sometimes it's a different type of a description in order. And all of these phrases are coming off of that wheel of words and phrases in order from least value to greatest value. Everything is very interconnected. That's why I wanted to kind of have something like this on the review. I wanted you to go over these words, phrases, and organize them in your own way. Okay, here on the side. All right, when we were writing domain and range, one way we were writing the domain and range was we would use something called set builder notation. Now, another reason I like to make these videos for you guys is because every textbook, teacher, tutor, whatever, might refer to things using slightly different phrases, and that's okay. But when you're trying to search something, if you're not comfortable with the phrasing, you might not think it's the right topic, and you might not realize that video could help you. So I just try to use the same vocabulary all the time, but I also try to tell you as much vocabulary as I can. So I'm just giving an example of what set builder notation would look like. So it looks something like this, and it means just those numbers are listed, whether it's in the domain or the range. Other things that we can kind of include here is you may look at this stuff as, sometimes you can use this when you're dealing with discrete information. Okay, discrete values, which are more or less your counting numbers. You can't have half of something, you don't have every single value, but you could have discrete values that are decimals if you're dealing with money out to 2 decimal places. You know, you can't have any single decimal number. You really can only round out to 2 decimal places, unless, like we spoke about, in certain business transactions and with like things like oil, petroleum, gasoline, whatever, they may round out further because people are spending far more money, but they break it down maybe by gallon, and you're buying thousands or millions of gallons of gas as a company over the course of a year. So the decimals may go out further. So it's a very abstract conversation to have here. Another phrase we might associate with this is finite. A finite list cannot be going on till infinities, so it's sort of the opposite of infinite. So I'm going to write can be counted. Okay, so these phrases are going to connect with each other here. Okay, so I'm going to box these off. They go together. When you think of them, you're going to think of them together. Now, sometimes that's a good thing. Sometimes it's a bad thing. Like when we talk about, for example, area and circumference of a circle, what happens a lot of the time is people mix up those formulas because you learn them at the same time. So then you think, oh, area is this formula or circumference is that, because you're grouping them together and you're generalizing or making an association. So I'm trying to make this so that we could avoid a situation like that. Like, yes, they go together. You learn them in the same unit, but they are different. What's the other notation that we used? We can also use, which is going to be, to me, really helpful in the future if you take pre-calculus or calculus, use interval notation. So I'll start that over here. And this one's going to go a little bit more intense as we go down. So I might need more space. I might move it up or zoom out a little bit. Use interval notation. Well, let's put an example of that. So an example might be from negative infinity, moving along until, say, -4. Maybe -4 is included. Union, that means I'm connecting it to another interval. I don't want to say set because really that's a set, so I have to watch my vocabulary. Then from, say, 0 until 23, not including either of those numbers. Union again. We can start again. From 27, maybe we go on until infinity, and maybe we stop. I'll make it go till infinity. Okay? So that's an example. Now, other phrases that we can talk about here, this looks more continuous. And even if you look up the definition we gave of continuous, continuous doesn't have to go from infinity till negative infinities, negative infinity until infinity. It could be continuous amounts within a certain window, okay? Continuous goes with the discrete values, so continuous values. And in respect to the finite, we can say oftentimes this is more infinite. We can have infinite sets. For example, the set of all real numbers is infinite, and it is a set. The set of integers. Integers actually looks like a Z with an extra line. Those are like -1, -2, -3, ... forever. 0, 1, 2, 3, ... it's a set. It's not every number. They are discrete values, but it is infinite. It goes on forever. So it is a little gray area. So I'm going to kind of connect that to those special cases. Infinite cannot be counted, right? I'm just doing it so cannot is one word, be counted. Now I'm going, oh gosh, I hate when that happens. I'm going to zoom out and, or scroll down really, or move this down, however I want to say this. And I'm going to talk about interval notation in regards to using things like greater than, less than, parentheses, brackets, and all that. Okay, so from my interval notation, I'm going to talk about symbols, etc. So maybe your mind automatically kind of thinks of using either parentheses or brackets. So really, I'm going to break it apart in that way. So here I'm going to talk about when we use the brackets. And by brackets, I mean these square brackets. And I'll put these in little clouds so that we really can notice those square brackets right there. And on this side, I'll put parentheses. And I'll even write it in parentheses. And again, nice little puffy cloud here. Okay, now building off of that, when do we use these things, right? You may have a pretty good idea. I did notice that some people do seem to be confused on this, so please make sure you know these really well. You want to use parentheses when it's something like a less than situation, okay, or greater than. That would mean it's not included. Brackets, on the other hand, is a situation where you might see something in the sense of less than or equal to. It means it includes that number, similar to greater. Oh, that's going to cut off, isn't it? Okay. Greater than, AN for than, or equal to. Okay, there's a reason I write full words. You don't want to change halfway to symbols, and why even write words at all, right? We want the words so we know how to read what we're doing. Okay, so we have this information. What else do we know? We might look at parentheses when we're seeing on a number line or on a graph. We might have an open circle. And I just use the word open. So open, I'm going to call this just open circle for right now. I am going to use a different word in a moment. And then here, keeping it all in order, this would be called a closed circle. Other words that we can use, and I did say, feel free to add your own words to the list. Excluded, up until, so it's like, oh, we're right up until 4, okay? Excluded, if I use excluded or excluding this value, then what word should I use over here? Well, that would be included. That one's a little easier to wrap our minds around. When else? So now we're going to write, we can use this. Oh, this one is a special case. When approaching, I can use the word, or inclusive up to the infinities. And I'm going to even write a little more details here on infinities, which is negative infinity and slash or positive infinity. I'm going to put a bullet point, okay? Bullet point for this. I know it's a little funny, but bullet point for that. Bullet point for these. Bullet point. I'll color the bullet points at the end, so it'll all be done. Okay. Now with the infinities, you'll never reach them up until you don't touch it. So you never reach the value. I don't want to say number because infinity is not really a number against the parentheses. Okay. Whatever number you put against the parentheses, you never ever reach it. A little sad love story, right? Parentheses. Okay. Whereas here, we do reach the value next to the bracket. You do reach it. Okay, you include it, you touch it, it's included. So the bottom two words that I would just like to add right down here is, we might call this an open interval. Okay, and this one we might call a closed interval. I did give you a packet that was sort of between lessons 1 and 2, and on the cover of that packet, I did talk about open intervals, closed intervals, half open, half closed. You can have a combination of these two. okay? They can come together and we can have something that's half open, half closed, sort of like up here. That's half open and half closed, this interval. This is an open interval, and this is half closed, half open, and so on, okay? So that, I believe I included all of the words and phrases on the circle. In the study guide, I also elaborated and added a few of my own. I'm going to color coordinate a little bit. I'll show an image of this again, and then that's the end of this part. All right, so here is just the color coordinated. I don't think that you need to memorize something like this. I honestly believe that if you just go through the motions of making it, pause, make it with me, that's enough to really help literally connect topics and vocabulary to each other. So we started with relations, so we could relate two or more variables, such as x and y. X and y, we're really talking about input, independent domain, output, dependent range. Domain and range, we could have our own discussion about. Functions are special relations. That's where f of x comes in as that notation right over there. And I may even want to kind of connect it to this red box over here. And f of x's or functions are where we use words like input and output, which I underlined in blue, over here to tie it up to this. Domain and range, don't repeat values. We list or describe in order from least to greatest value. We can do domain and range with two different ways. We use set builder notation or interval notation. Do you know when to use each one? What does each one look like? Set builder notation looks more like this. We use these curly brackets over here. It's a set of values. Usually they could be discrete values. They could be finite where you can count them. Where these, though, however, are special. These are actually infinite. This, again, is the set of real numbers. This is the set. So these are sets. Okay, sets. But they are, this case, these are special because these sets are actually infinite. But don't worry, I'm just dropping that gem into your head. Interval notation would look more like this. From negative infinity, obviously not including it. You can't get there until -4. And -4 is included. U stands for union. It's not a regular U with a tail. It's like a horseshoe shape. Pick up again right after 0 until 23. Neither of those are included. They are excluded from the domain. 22.9 repeating is included. It's silly to write that. We write this instead. Union. Pick up at 27 where it's included until infinity. These are more continuous values. These are continuous intervals even. Interval. We could be talking about infinite amounts that cannot be counted. Then interval notation, we can elaborate with some symbols and so on. When do we use parentheses and when do we use brackets? And I tried to just sort of highlight the most important things on that list. When you see symbols like this, I know we might not see them when you're analyzing a graph or a list, but algebraically when we solve later in the year with square root functions and with things like that, these are going to come up. Denominators, whatever. Open and closed circles, excluded versus included. The infinities are on this list. Here we don't reach a value. Here we do reach a value. We use the word open, describing this, and closed, describing this. And the little heart is because we said that they can come together. If you look at the cover of the one packet we used between lessons 1 and 2, we talked about half open and closed intervals. All right, I hope this helps.